So Eva will talk about making choreographies polymorphic.
Yes, Earl. So I'm going to talk about my paper about process polymorphism in choreographies. But before I get to the process polymorphism part, I'm going to explain to you what a choreography is. Choreography is something that looks something like this. It is a program which describes the behavior of an entire system and which is then compiled into local code for each participant in that system. So here, for example, you have A sends to B and then send to C, C computes something, C sends to B, etc. And for A, you get this code, and then so on and so forth. And why would you want to write your systems like this? Well, choreographies give you simpler, more readable code, which also makes it easier to reason about if you want to know the properties of your system. It guarantees that it is deadlock-free because everyone is in agreement about who should be communicating when, and similarly, there are no communication mismatches where one participant expects to get a string, for example, and another person, and the person sending thinks they're supposed to be sending them an int. But the choreography I just showed you was not very functional, and this is ICFP. So what does a functional choreography look like? Well, it looks something like this. This is Chorλ, which we developed. And Chorλ is the first higher order choreography language and also the first functional choreography language. So here we have a choreography in Chorλ where we have, which is parametric on a string at the buyer, which is the title of a book that the buyer wants to buy, and a function also at the buyer, which determines whether the buyer, they are willing to purchase this book at whatever price they're given. So what happens in this choreography is that the buyer communicates this title to the seller using the com function, and then the seller looks up what the price of this particular title is and communicates this back to the buyer, who decides whether they want to buy the book, and then they inform the seller. Now this, when we presented this, one of the main things people asked us about is, what about polymorphism? It's all well good to be able to write this, but surely the seller doesn't want to only be able to have this interaction with one buyer. Surely they want to be able to interact with any number of people who might want to buy a book. So this is why I'm presenting PolyChorλ, where we have polymorphism. So here our choreography is parametric on B, which is a process, and it performs the role of the buyer. So what are the features of PolyChorλ, or the polymorphic choreographic lambda calculus? Well, it adds the communication of distributed values, so values which are not located entirely at the sender can now be communicated. They can communicate only their part of the value. It adds type polymorphism, and it adds process polymorphism, and it's based on system F omega. And I will explain to you why it is not just system F, because it needs to be system F omega, as it turns out. But first, let's see what communicating a distributed value looks like. So here we have the value is a function, we call it f, which takes an int at a and communicates this int from a to b. And we want to communicate this function f from a to c. Now, at a, what you get is this function f looks the same, except that we're sending instead of having the whole communication, and we say just know that x is an int, rather than needing to annotate about where x is. And the communication C also just becomes, we're sending it to C. But at B, which is more interesting, since B is involved in F, it needs to have do a little substitution where the receive from A becomes a receive from C. Also note that in F, we say that X has the type bottom, which means that X is located somewhere else, but we need to have it for structural reasons to make sure that the choreography can be typed and stuff. And we replace it then again with bottom, which is, again, that's a value that is somewhere else but is needed to make sure our choreography has the right structure. So that's pretty simple. We were pretty happy with our little work getting that to work, so we started working on type polymorphism. Now what we were hoping to do was, we were hoping to have rules that look something like this, where you have a standard type abstraction, you get a faulty something type, and you add t is type to lambda, and there you go. And our com, we were hoping to keep more or less the same communication typing rules that Chorλ had, which is to say that the type we're communicating can't already be located at the receiver, so B is not in the mentioned processes of tau, but otherwise, since we're now sending distributed values, we can have anything in tau. And then we just do a substitution on all instances of A to get the new type. So we thought this was going to work. We made the minimum example of combining these, and we immediately ran into a problem. Because as it turns out, when you have a process when you have choreography that is parametric on the type that is being communicated, you can't just do the substitution of A for B on the value T, because you do that on a variable, sorry, not a value, a variable, you get the same variable, and our thing has not moved, even though if T turns out to be instantiated with something mentioning Alice, then it should be moving all of those things to Bob. So that is why we wound up needing to both have type level functions and to have process polymorphism. So now instead of being annotated with the type of the value being sent, our com is annotated with a type level function which takes the sender and returns the type of the value being sent, or it takes the receiver and returns the type of the value after it has been communicated. So now what our little choreography looks like this instead. And that does not immediately run into any problems, so let's try to see what we can do with this. So what happens if we instantiate it like this? We have to make our little type level function, which takes a process P and creates an int at P. Then the whole thing becomes an int at Alice to an int at Bob. Perfect, that's what our communication should be doing if we're communicating int. However, what happens if we're stupid and we instead write our type level functions like this? It takes a process, throws it out, creates an int at Alice. Well, then our int at Alice remains an int at Alice after being sent, except that it doesn't in the semantics, because the semantics aren't looking at all of these types, it's just looking at our int and going, okay, well, that's at Bob now. So how do we solve this problem? Well, here's the conclusion to our com problem. We need to restrict the possible variables and process names that can appear in our tau. And the way we do it is actually, we do it backwards. We restrict the ones that can appear in our two sender and receiver. So we say that the mentioned processing tau and we have a restriction on the kind, which is on everything that appears freely in tau, and then when we're abstracting a type, we have this fairly complicated rule, unfortunately, where we not just add x with its kind to the lambda, we first need to remove x from any existing restrictions on any kinds, and then we add a restriction on x to the kinds of anything that is in the restriction we get here. So rho is a set of processes. And yeah, that solved our problem. So how do we compile this? How do we generate local code? Well, here we have a new f kind of like the previous one. What this f does is it takes a process p, and it communicates the int 5 at a from a to p. And it's got, the functions it needs to do that. And like before, we send this function from a to c. So what does that look like at a? Well, we need to determine whether p is a, because a needs to behave differently. So that's why we have this little am I p. If I am p, well, then I am sending from myself to myself, which is an identity function, obviously. If I'm not p, then I need to send to p. And we send all of this to c, as before. But if at a process that is not a, well, everyone needs to determine whether they are p, because nobody knows when we're generating the code whether they are p. So everywhere gets this am I, and if I am p, well, then I need to receive from a, and if not, then I'm doing nothing. This leads to a lot of states, as you can probably guess, because everyone gets this am I, and it it's a conditional, so you're generating code for the entirety of whatever p is involved in. But we would argue that that's kind of inevitable if you have this sort of polymorphism. Because even if you're writing this code manually for A and B and C and so on, well, if you're writing it under the assumption that you don't know whether you're going to be P or not, well, then you need to write a conditional to determine this. And at least with this choreography, you don't have to do it manually. It gets generated for you, which means that this kind of stuff, if you're OK with having more code, is somewhat reasonable to write. So that's nice. So I'm just going to go through more details about how we generate this code. So our distributed implementation of a choreography M is a parallel composition of every process mentioned. And we generate the code using this little function here. So for example, for com, what you generate is you look at the sender and receiver, and you say, if they are both me, well, then I am making a little identity function, and I got to have the right type, which I also can project. And if I'm the sender but not the receiver, then then this com is a send. If I'm the receiver, then the com is a receive. If I am involved in the value that is being communicated, that is to say I am mentioned in tau, or my tau is not somewhere else completely, then what I get is a substitution. And if neither, then I just get bottom, and we collect the bottoms as we go, so that if you have a bunch of them in some complicated structure, then they just become one. Another example, here we have our type abstraction. So you can see we generate the am I if the kind of X is a process with or without a restriction, we don't care. If the kind of X is something that is restricted on the process we're currently projecting to, then we just throw the abstraction away completely, ignore it, and otherwise, yeah, we made it. This is a type, and it's a type that is potentially at the process we're currently generating code for, so we make a type level abstraction. So to conclude, we have the first choreographic language with full type polymorphism, that is to say not just polymorphism of local types, but of full types with annotation of where they are. It's first language with process polymorphism, and we're the first to communicate distributed values. And this has taught us that if communication is a function, then you can't do full type polymorphism without also having process polymorphism and type level functions. And if you have process polymorphism and communication of distributed values, then you need some sort of way of restricting the process that can appear in a certain type. Yeah, if you read the paper, you'll find the full thing. We got full semantics, full typing, kinding, generation of local code, and we got some proofs of the standard choreographic properties, operational correspondence between the global and local semantics, and deadlock freedom proof. Yeah.
questions? So the inference, there's a question. Very good.
Just a quick question. So the am I predicate looks like it's dispatching on the type.
Yes.
So that's different from f omega, right? So there's
Different from what?
that's different from f omega in the sense you haven't got an erasure property.
Yeah, this is kind of an extra thing. The AMI is not part of f omega, but yeah, it matches on the process names. So each process knows its own name. So when it looks at one, it can tell if that's me or not, basically.
Hello, James Chapman, Input Output. I just wondered if you've considered formalizing this work, because the type system looks a bit tricky. So.
Yeah, we have sort of considered it, and but not yet, at least. Yeah.
Thank you.